Welcome to the EuclidIQ webinar titled Rhythm, the Content Adaptive Transcoder with a Human Touch. My name is Nigel Lee, and I'm the Chief Science Officer at EuclidIQ based in Concord, Massachusetts. This work represents the joint efforts of the algorithm team and the product development team at EuclidIQ. Before I begin, let me take care of some administrative items. First, if you have any questions during the talk, feel free to enter your questions in the comment box on the webinar registration page. Second, the recording of this webinar will be available for some time after the live talk at the EuclidIQ YouTube channel, so you can review the information from the video at your own pace. With those items taken care of, let's begin the talk. In their constant quest to provide the best quality of experience, video distribution companies have increasingly turned to a technology called adaptive bitrate or ABR streaming. In ABR streaming, an encoder is configured to provide multiple encodings of a video at different frame sizes and bit rates. An adaptive video player then detects the user's bandwidth and CPU capacity and selects the best version of the video to stream based on network conditions. So, for example, if network speed is slow, the player switches to a smaller frame size of 720p or even 480p and the corresponding lower bit rates. When conditions improve, the player switches back to a larger frame size and higher bit rate. ABR streaming theoretically minimizes buffering and artifacts during playback while ensuring good video quality for given network conditions. The set of frame sizes and bit rates at which a video is encoded for ABR streaming is called an encoding ladder, in which each frame size is encoded at 1 or 2 bit rates. Shown here is Apple's historical encoding ladder for the HTTP live streaming or HLS streaming protocol. Other streaming protocols exist, including MPEG-Dash and Microsoft Smooth Streaming, but all standard ABR streaming protocols follow an encoding ladder, encoding all videos at a set of fixed bit rates based on frame size, which comprise the rungs of the ladder. However, in video encoding, one size doesn't fit all, and to encode all videos at a given frame size at a fixed bit rate, regardless of content, isn't always efficient. We know that for low complexity videos, good quality encodings can be achieved at lower bit rates than for high complexity videos. For example, the screenshot on the left comes from a low complexity video of a baseball player sitting on a bench and looking up at the camera a couple of times. Encodings of this video can achieve excellent quality at 1.8 megabits per second. By contrast, the screenshot on the right comes from a high complexity video in which several hundred runners are running toward the camera. Encodings of this video struggle to achieve satisfactory quality even at 7 megabits per second. The natural question that arises is, can the encoding bitrate for a given video be effectively adapted based on the content of the video? The answer is yes, and how that is done best is what the rest of this webinar is about. Before I go on, I want to point out that the A in ABR streaming refers to adaptation to network conditions. The adaptation we're discussing here is content adaptation, which is a second type of adaptation that can be added to standard ABR streaming. Taking a step back, our goal is to achieve the optimal video streaming experience. To better understand how we can do that, I want to make an extended analogy with achieving the optimal driving experience in a futuristic self-driving car that might have to drive through several different environments, such as city traffic, a mountainous dirt road, and a winding inclined highway. It's useful for this car to have an optimized engine that achieves the best driving performance in any given environment. But it's also useful if the car contains adaptive cruise control technology that senses the upcoming environment and customizes driving instructions to provide optimized handling and mileage. The critical point is that the two components work together to achieve the best possible driving experience. The intelligent algorithm figures out the best driving instructions, and the optimized engine puts those instructions to the best use. By analogy, there are two similar components to an optimal video streaming experience. The car's high-performance engine is equivalent to the encoder, which seeks to provide the best video quality for any given bit rate. The car's intelligent adaptive cruise control is equivalent to a content adaptation algorithm, which determines the best encoding bitrate based on the video content. So in terms of optimizing one's video streaming experience, there are two pathways for improving on a standard configuration with a basic encoder and a typical fixed bitrate encoding ladder. You can improve the engine, replacing the basic encoder with an enhanced encoder that provides better video quality at any given bit rate, but you'd still be left with a fixed bitrate encoding ladder. Or you could develop an intelligent algorithm deriving a content adaptive encoding ladder that determines the best bit rates for any given content, but you'd still be left with a basic encoder. But a total solution for truly optimizing one's video streaming experience includes both an enhanced encoder and a content adaptive encoding ladder. With that introduction, I'd now like to present Rithm, EuclidIQ's content adaptive transcoder with a human touch. As a total solution for optimizing video streaming, Rithm has the two essential components I just discussed, an enhanced encoder and a content adaptation algorithm. Our underlying encoder applies perceptual quality optimization, or PQO, that reflects the human visual system to produce the best video quality at any given bit rate. Our content adaptation algorithm is called SABRE, or Signal Adaptive Bitrate Estimation, which estimates the encoding bitrate that will achieve a desired quality level for a given encoder and a given video. The combination of PQO and SABRE within Rithm forms a content adaptive transcoding solution that saves maximum bandwidth for any given video content while maintaining a desired quality level, leading to an optimal video streaming experience. What distinguishes Rithm from other content adaptive transcoding solutions is what we call the human touch. PQO within the encoder optimizes human perceptual quality in the encoding decisions, and SABRE models video quality based on human subjective test scores. Put another way, while many solutions on the market claim to use artificial intelligence, Rhythm's version of AI is based on human intelligence. I'm now going to describe in more detail the two essential components of Rithm, the first being enhanced encoding based on perceptual quality optimization. Why is PQO important? Traditional encoders derive a best encoding of videos based on artificial approximations. They use a mathematical definition of quality and perform block-by-block optimizations, mostly optimizing each block independent of neighboring blocks. However, this isn't the way humans perceive video and often results in too many bits spent on less noticeable areas or too few bits spent on more noticeable areas. By contrast, the perceptual quality optimization, or PQO approach to encoding considers the way the human visual system perceives a video using a subjective definition of quality and spatial optimization that takes entire frames into account. The result is more bits spent on areas more noticeable to viewers and fewer bits spent on less noticeable areas. Now, others have tried to implement PQO, but in comparison, our approach is more sophisticated than some of the simpler PQO techniques being used today, and more flexible than some of the more complex PQO techniques attempted in the past. We feel our PQO approach provides a good balance between sophistication, simplicity, and speed. At the heart of our perceptual quality optimization is what we call a unified importance map that combines both spatial and temporal information to predict the key areas in each frame that are most noticeable to the human visual system. The unified importance map makes use of 8 different spatial and temporal inputs listed here to determine perceptually more important areas of the frame in red and perceptually less important areas in blue. Once the unified importance map is calculated, we then automatically adjust the encoding quality based on the map values. Here's a closer look at the unified importance map. Red areas, including in this example the girl's cheeks, neck, and arms, some of the leaves, and most of the sky, are determined by the unified importance map to be perceptually more important to the human visual system, so we encode those areas at higher quality than a standard encoder would. Blue areas, including the girl's eyes, teeth, and hair, plus most of the leaves, are determined to be perceptually less important, so we spend fewer bits for those areas and reduce encoding size relative to what a standard encoder would use. This diagram shows how PQO fits into standard codec architectures. PQO integrates into the prediction and quantization modules of the encoder, taking inputs from the prediction module and outputting modified quantization values on a block-by-block basis for each encoded frame. PQO produces bit streams that are fully standards compliant, able to be decoded by any standard decoder. Additionally, PQO requires minimal computational overhead beyond what standard encoders need. At this point, I'd like to switch gears to talk about content adaptation in general and Rithm SABRE algorithm in particular. To review why content adaptation is important for video streaming, historical encoding ladders that encode all videos at a set of fixed bit rates based on frame size are straightforward, but are often either inefficient, encoding low complexity content at too high a bit rate, thus wasting bits, or insufficient, encoding high complexity content at too low a bit rate, resulting in poor quality. Content adaptation addresses this by adapting the bit rates in the encoding ladder to the video content. There are several different types of content adaptation algorithms that trade off modeling precision, that is, how accurately and how often the video content is modeled, with computation time. The less precise algorithms at the bottom of the diagram require fewer computations, while the more precise algorithms at the top require more computations. This table gives a general overview of the different types of content adaptation, from the least precise at the top of the table to the most precise at the bottom. Per category adaptation seeks to vary the encoding ladder by semantic category, with one ladder for animation, another for sports, and still others for drama or action movies. The problem with this is that the semantic categories aren't homogeneous. For example, a baseball game has a lot less continuous action than a basketball game, though both are sports, and it's unlikely that a single encoding ladder will be optimal for both. Per title adaptation, which Netflix popularized a couple years ago, seeks to vary the encoding ladder with each video. So among action movies, for example, there would be one encoding ladder for Star Wars: A New Hope, another for Avengers, and still another for Black Panther. The challenge here is that long-form videos are often not homogeneous within the video. For example, action movies often intersperse high-complexity action scenes with slower, low-complexity dialogue scenes. So a per-title fixed encoding ladder still might be suboptimal for some portions of the video. Per segment adaptation divides a video into segments and varies the encoding bitrate per segment. The segments can either be time-based, that is, all segments are a fixed duration of some number of seconds, or scene-based, that is, segments vary in duration based on the length of each scene. Both of these face their own challenges. For the time-based techniques, there can still be mixed content within the segments. For the scene-based techniques, the scene cuts may not align with the segment boundaries required by streaming protocols. The bottom two types of content adaptation, per frame and per block, occur within the encoder and seek to vary encoding quality either frame by frame or block by block based on analysis of statistics within the video. These techniques face the challenges of high computations if they are too complex, or poor accuracy if they are too simple. In general, finer granularities of adaptation provide greater compression benefits, that is, higher video quality and more bandwidth savings, at the cost of increased computations. To place Rhythm's two essential components into the context of this table, PQO that I already discussed is a per-block content adaptation within the encoder, and Saber that I will discuss is a time-based per-segment adaptation. Before I describe Saber, let's talk about what makes a good content adaptive encoding algorithm in general. Any content adaptive encoding, or CAE, algorithm requires two components. First, a quality metric that automatically estimates encoding quality based on underlying statistics in the video. And second, an implementation that turns those quality estimates into bitrate estimates, finding the lowest bitrate that achieves the desired quality level for maximum bandwidth savings. Now, it's fairly easy to come up with a working CAE implementation, but it's not easy to come up with an implementation that works well. First, the quality metric must accurately model subjective video quality. Otherwise, the estimated encoding bitrate may be too low, leading to poor video quality and a reduced quality of experience. In other words, larger bandwidth savings is irrelevant if the result is poor video quality. And second, any model must generalize well and be accurate across many types of videos with different spatial and temporal characteristics and different frame sizes. In other words, it doesn't help to develop a model that works well for some types of videos, but not others. With that background, let me now explain why Rhythm's content adaptive transcoding solution is unique. Rhythm's Saber algorithm models video quality by tuning its underlying statistics to human subjective test data. It's widely agreed that mean opinion score, or MOS, from subjective tests is the gold standard of video quality metrics. However, while other content adaptive algorithms use metrics that try to approximate MOS, Saber is designed for it, making use of a MOS predictor, or MOS-P metric, that is calculated using MOS data from actual subjective tests. It's important to note that MOS-based modeling requires the ability to generate subjective test data quickly and accurately, which is why most people avoid it, since subjective tests are usually slow and expensive to conduct. However, we've worked hard to develop a unique subjective test methodology that does generate subjective test data quickly and accurately, and this is what enables us to employ MOS-based modeling within Sabre. Now, Sabre can model video quality for any encoder, but it complements our PQO encoder the best since there is a human touch at both ends of the processing. PQO encoding that optimizes human perceptual quality, and Sabre modeling based on human mean opinion score data. Overall, then, Rithm achieves maximum bandwidth savings for a desired quality level by combining accurate model of video content via Sabre with the best encoding of video content via PQO. Here's a conceptual block diagram of the Rithm workflow. The customer uploads an input video file and provides some input parameters defining the encoding environment, including a nominal encoding ladder consisting of a set of desired frame sizes and maximum bit rates for each frame size, as well as a desired MOS quality level. The input video is then sent to the cloud, where the Rithm Cloud Transcoder uses the PQO plus Sabre combination to generate bandwidth-optimized encodings of the video that maintain the customer's desired quality level. The Rithm transcoded video is then sent to the customer's output bucket. This workflow is designed to be simple and easy to use, and we'll take you through the actual Rithm API in a future webinar. I'll now provide some examples of Rithm in action. First are a couple of examples comparing Rithm for 1080p videos against Amazon's industry standard elastic transcoder. In the top example, the input video is a 3-minute portion of the standard evaluation material, or STEM video, used by the motion picture industry to evaluate video encoders. The left-hand side shows Amazon's elastic transcoder encoding the video at 5.8 megabits per second, which is a common ladder bit rate for 1080p videos. The right-hand side shows Rithm using PQO plus Sabre encoding the video at 4 megabits per second. The quality of the videos is the same, but Rithm provides a 32% bandwidth savings relative to Amazon's elastic transcoder, which is impressive given that the STEM video is highly complex and designed to be challenging to encoders. In the bottom example, the input video is a 2-minute mix of various HD video content, and here Rithm provides a 42% bandwidth savings relative to Amazon's elastic transcoder while maintaining the same video quality. Again, by applying PQO to enhance the encoding and Sabre to adapt the encoding to the video content, Rithm produces maximum bandwidth savings at a given video quality level. I should mention that we plan to set up a web page where you can stream all the encodings in these two comparisons, both Rithm and elastic transcoder, so you can judge their quality yourself. Now I'll show a few examples for a full ABR encoding ladder of 6 rungs. The first example is for a 21-minute video of animated content at a desired MOS quality of 3.8 on a scale of 1 to 5, 5 being the best. The capped bit rates for the encoding ladder, as specified by the customer, are shown in this third column. Note that these bit rates are different from the HLS ladder bit rates that I showed earlier. Rithm's estimated encoding bit rates are in the fourth column, resulting in the bitrate savings percentages in the last column. Overall, Rithm achieved a 76% bitrate savings over the fixed ABR ladder, and it did that while achieving excellent quality for the output streams, above the input desired MOS. In this example, it's possible that the encoding bitrates could have been reduced even further while maintaining acceptable quality, but Rithm maintains a safety margin to ensure that its bit rates are not underestimated, and the bitrate savings were very large in any case, 76%. The next example is for a 53-minute video of mixed HD content, again at a desired MOS quality level of 3.8. Here, Rithm's overall bitrate savings was 47% over the fixed ABR ladder, with the quality of the output encoded streams judged as good, which corresponds to a MOS of 4, and met the desired quality level. However, upon viewing the output streams, the customer might decide that the quality needs to be higher than 4. In that case, the customer can send the same video to Rithm, but with a higher desired MOS quality of 4.25. With this higher quality setting, Rithm's overall bitrate savings over the fixed ABR ladder was lower, though still 14%. However, the quality of the output encoded streams was now judged as very good to excellent, equivalent to a MOS of 4.5. Thus, by varying the desired quality setting at the input, the customer can use Rithm to trade bandwidth savings for higher output quality. In summary, Rithm is EuclidIQ's unique content adaptive transcoding solution. It contains two essential components, an enhanced encoder and a content adaptive algorithm. Rhythm's underlying enhanced encoder applies perceptual quality optimization, or PQO, that reflects the human visual system to produce the best video quality at any given bit rate. Rhythm's content adaptation algorithm, called SABRE, or Signal Adaptive Bitrate Estimation, models video quality tuned to human mean opinion score, or MOS data, from subjective tests, which provides the best and most accurate model of video quality. Thus, Rithm combines an accurate model of video content through SABRE with the best encoding of video content through PQO. And the PQO plus SABRE combination provides maximum bandwidth savings for a desired quality level. I would also point out that in straight encoding comparisons at fixed bit rates, our PQO enhanced encoder can also provide visibly better quality than standard encoders. So the Rithm solution provides either bandwidth savings while maintaining quality in quality constrained settings, or quality improvements while maintaining bandwidth in bandwidth constrained environments. The ABR streaming examples that I showed in this talk demonstrate Rhythm's potential bandwidth savings of 15 to 75% relative to a fixed ABR ladder while maintaining desired video quality. As with all content adaptive transcoding solutions, the amount of bandwidth savings Rithm can provide depends on the video content as well as the customer's desired quality setting. Besides bandwidth savings, additional benefits from applying Rithm include reduced video start times, less buffering, and lower network and storage infrastructure costs. As for next steps, first, we welcome you to try out Rithm for yourself by requesting a demo at this link. Also, as I mentioned earlier, we plan to set up a web page with some example Rithm transcoding so you can stream them and examine their quality for yourself. If you're interested in that, please let us know. Second, if you'd like to talk with us about Rithm, our team will be at NAB from April 10 to 13 and would love to meet with you there. And third, please contact us if you have any questions by sending us email or visiting our website. That's it for the main webinar content. Thank you very much for your attention. I'll now address some of the questions that came up during the webinar. The first question is, which codecs does Rithm work with? So we designed Rithm to work with H.264. However, there is nothing about the PQO or SABRE algorithms to prevent either technology from being integrated with VP9, HEVC, or AV1, although the algorithms would likely need to be tuned for each new codec. The next question is, how fast is Rithm? So to date, we've been focused more on compression performance than computational speed, but with some basic parallelization, we have both PQO and SABRE running at near real time on Amazon. If we were to focus on computational speed, we feel confident that we could achieve real time. And that seems to be it for the questions. If you didn't get your question answered during the webinar, please send it by email and someone will be sure to get back to you. Thanks again, and we hope to hear from you soon.